We're good?
Yeah.
All right. So yesterday we did completing the square. We did enough examples that I think. And again, guys, just because the structure and how much time we have, going through all the different variations, all the possible types of examples is not feasible. All right. But if you go to my website, there's a lot of videos of them doing extra quadratic formulas, extra completing the square, extra AC methods, all that kind of stuff. So I give you the nuts and bolts and as many examples as I can during class, but if it's not something that's sinking in right away, there are things you can turn to and get more examples, okay? So that being said, I think we finished yesterday with example 3, walked through that. But I want to show you guys that the fact that it should not matter what A, B, and C are, okay? It should not matter whether it's 2, 7, and 4 for our coefficients. And then see what happens if I complete the square with kind of total disregard to what those values are, okay? Just let them be arbitrary real numbers. So I'm going to say, I'm going to start with A, x squared, plus bx, plus c is equal to 0, okay? A, B, and C are real numbers. They're just arbitrary, don't care what they are, okay? Now I'm going to complete the square with this. If you remember yesterday, two first steps were independent of one another. You can move C to the other side, move your constant to the other side, or you can divide both sides, or sorry, all parts by A, all terms by A. I'm going to do both those things at the same time. So when I do that, it should look like this. Okay? Move my C term over, divide everything by A. Alright? Obviously, it's a lot easier when we have numerical values and we can see it, you know, it's simplified down to something like maybe 2 or 6 or something like that. But instead, we have B over A and negative C over A. Alright? But we're going to do our algebra. We're going to go ahead and complete the square with this. If I complete the square with this, remember the way we complete the square is we took half of this term. Half of that B over A. Okay? Well, if I have B over A, and I take half of it, divide it by 2, which is the same thing as multiplying by what? 1/2, right? If I multiply that thing by 1/2, does it just give me B over 2A? Okay? So that's having my middle term, my B term. Now I need to square it, right? So when I square it, hopefully we remember these laws of exponents we talked a little bit about yesterday. If I square that, I'm going to square this out, it gives me B squared. Okay? But now, when I have that denominator, it's a product of things. So now that I have the 2 raised to the 1 power squared, and I have A raised to the 1 power squared. Does that make sense? So I need to make sure that that power of 2 goes to both those objects down here, because it's a product. So that's going to be 4A squared, okay? So that is completing the square. That is the process that is going to allow me to add to the left-hand side and add to the right-hand side so that I end up over here with a perfect trinomial. Okay? And that perfect trinomial is going to look like this. It's going to be, remember we talked yesterday, it's always going to be x because that's always going to be a 1 right there. This sign here is always whatever that sign right there is. And then the object that goes here, remember, it's the term that was in the middle after you took half of it. Okay? So B over A, and I take half of it, that gave me B over 2A, right? Okay? And we'll square that. And before I even go on, I'm going to just kind of convince myself of this. If I square that, it gives me x squared. If I square this term, okay, we already kind of talked about it, it's going to give me B squared over 4A squared, so that's good. Now the only thing is if I multiply these two things together, I get BX over 2A, right? But if I double it, it'd be multiplying by 2 over 1, right? What's going to happen with the 2 up here and the 2 down there? It cancels, it leaves me B over A times X, right? Is that what I had here? And so I know that this is right, because when I FOIL that out, I get exactly what I started with. Okay? Now on the right-hand side, we've got that thing right there. 2 fractions, correct? let's write it down. Let's condense it to one fraction. What do I need in that situation if it's going to be one fraction? We're going to add these together. What do I need? Common denominator. What's the common denominator going to be here? 4a squared. Okay? So does this one need to be multiplied by anything? No? Does this one? Yeah, this needs to be multiplied by 4a, right? Multiply by 4a, multiply top by 4a, right? So now up top I get negative 4ac. Okay? On the bottom I still have 4a squared, and then this one I'll have my b squared. Once we get to that stage, now we can use the square root method, right? Square root both sides. Creates a plus or minus. Now over here, obviously those are going to cancel, which is going to be x plus b over 2a. Okay? Now on the right hand side, and we discussed this yesterday, when I have a fraction underneath a radical, I should be able to take the numerator under its own radical. That's because of the law of exponents. Numerator under its own radical. Denominator under its own radical, right? Is that doable? All right, now I just want to look at that numerator real quick. We have the commutative property with addition. We can flip these things around, can't we? If I put this b squared first, I just want to do that. So I'll rewrite this as positive b squared minus 4ac. Hopefully that's something that's familiar to you. You've seen that before. Look at that denominator. What kind of number is 4? Perfect square, right? What kind of number is a squared? Perfect square. Okay? No matter what a is, it's arbitrary, but if I square it, it turns into a perfect square. So, square root of that is 2, square root of that is a, right? Let's rewrite that. That's 2a. Now remember what we're trying to do. We're trying to solve for x, right? That's what the quadratic formula, that's what completing the square is doing. It's what all our factoring is doing for us. So we're going to solve for that thing right there. It's going to move that to the other side. So it's going to look like this. Subtracting to the other side. Should be the opposite b, or 2a, plus or minus now. B squared minus 4ac over 2a. So now on the right hand side you have two ratios, right? What's nice about those two ratios? They already have that built-in common denominator, right? So we should be able to add the numerators and set that thing over that common denominator. And what do we develop there? Quadratic formula. Okay? So that's the algebraic proof for the derivation of the quadratic formula. What do we do to get that? We use completing the square process, right? So every time that you take that thing and you start plugging B's, A's, and C's in, understand that you are effectively using the completing the square process, but you're almost kind of circumventing all the work that is required in doing that. Does that make sense? Okay. But I think it's good for us to visualize where some of our formulas are coming from, especially if you're a person that knows, hey, I'm going to go to a major that has a heavy math background, because you're going to get into courses where, you know, that's what you do a lot of times. Okay, you go through the derivations, you go through the reasons of why something is the way it is. Okay, not so much here's a formula, just plug numbers into it and see what all our answers look like. Okay. But we end up wanting to know why things work. Okay? So now that we've got the quadratic formula, we should be able to do some of these problems down here at the bottom. Okay? And as we do these, I want to make sure that we kind of discuss the things that can happen. Okay? Because remember, your quadratic formula is your catch-all, right? It's the process that will factor any quadratic equation we come across. Okay? So it's going to always work, but it's not always the quickest, okay? And when we get certain types of answers, that should tell me, is quadratic formula the only method that would have worked, or is there another approach that might have been quicker? And your answer should be able to tell you that, okay? And I'm kind of walking through some of that as we do this first example, okay? During this first example, all you got to do is identify your A, B's, and C's, right? We've done this. Okay, so there's my A, there's my B, there's my C. Okay? Now when I put those braces there, I'm taking the sign with them. Okay? I've had people in the past go through an entire year and they end up being a pretty bad grade at the end of the year. Using the quadratic formula, because we use it a lot. We use factoring almost all the time in this class. Almost use it all the time in calculus. And they want to use the quadratic formula as kind of their go-to method, which is fine. But they didn't know how to use it. They didn't know that I'm not going to use just 3, 5, and 1. I'm going to use 3, -5, and -1, right? Whenever I'm looking at an equation, the terms have a particular sign with them, and I got to pay attention to that. It's like you, whenever you go somewhere, you take your name with you, right? You take your first name, and you take your last name, or you just leave one of them somewhere. Take them both with you, right? Okay? So when I'm going to take these numbers, I take the first name, which is the sign, the plus or minus. I take the last name, which is actually the numerical value, okay? So make sure you're doing that and you're paying attention to that kind of stuff. So here I've got x. Okay, if I go opposite of b, so that's b, -5 is b, so opposite of that would be +5. Okay, now when I take b squared, I don't really care whether it's positive or negative, because what's going to happen when I square anything? Turns into positive, so I get 25. -4, now a was 3, c was -1. There's where I got to make sure that I have my -1. Because now when I start going through my order of operations and simplifying that radicand, that negative is very, very important for what we're doing. And then 2a on the bottom would be 6. Okay? And that's ultimately your answer, but it's not in the simplified version that we're interested in, or that we need. So now when I look at this, okay, so we got to do the multiplication first, right? That's what PEMDAS tells us, right? So we got to do -4 times 3 times -1 first. Well, you've got 3 terms that are being multiplied together. 2 of them are negative, so what's that going to turn that product into? A positive, right? So that set right there turns into a +12, okay? Maybe you're a person that just wants to look at that. Okay, don't look at the sign of -4. Let's just say 4 times 3 times -1. Well, 4 times 3 is 12, times -1 is -12, right? So then you have minus -12. What's minus -12? +12 again, okay? So we've got plus 12 in there. So what's 25 plus 12? 37. And right there, that number tells me that this thing is only factorable using either completing the square or the quadratic formula. Okay? It tells me that the AC method would not have worked, and the product sum technique would not have worked, at least efficiently. Okay? If I were to use those, I'd probably have to think outside the box a little bit. And basically what it means is, if I get my answers and I'm left with a radical that does not simplify and essentially disappear, okay? If I'm left with an irrational component to my answers, then that tells me that my only technique would have been the quadratic equation. Okay. Now there's some things that we got to pay attention to. If you want to, you can rewrite this as 5/6. Okay, because that's a common denominator. Does that make sense, everybody? That's a common denominator of 6. And if I want to separate, then that means I put each component of the numerator over that 6. So I could go plus or minus then radical 37 over 6. Being able to do that and being able to understand that is essential, because what happens is that we end up eventually getting questions that look like this or answers that look like this. Let me find my eraser. Let's say that we have a solution at some point that looks like, I don't know, let's go 6 plus or minus 3 radical 2 all over 2. Okay? And what happens is a lot of people want to just start canceling things. Well, 6 and the 2 cancel out, all that kind of stuff. And they want to write this, they just want to do this. Boom, boom, 3. 3 plus or minus 3 radical 2. Okay? That cannot be done. And the reason that cannot be done is because this numerator is a sum, which ultimately looks like this if I break it apart. 6 over 2 plus or minus 3 radical 2 over 2. Does that make sense? Now these can cancel. If I want to leave it as 3, that's fine. But can those cancel? No. Okay? Because if I look at that, what that really means to me, guys, is 3 over 2 times radical 2. And we know 3 halves doesn't simplify it. Okay? So, if I want to leave it as one fraction like this, I can't simplify that any further. If I'm willing to separate, then I can separate it, and I can write it that way, plus or minus. Okay? But I can't just cancel the 2 and the 6 because of that sum. All right? Now what happens eventually is that we say, okay, well, what happens if we have something like that? Well, now, because there's a factor of 2 there, and a factor of 2 there, and a factor of 2 there, then absolutely you can do that. That goes to 3, that goes to 1, and now I can rewrite this as 3 plus or minus radical 2. But the reason I can do that is because it's actually 6 over 2, 6 over that, plus or minus 2 radical 2 over that, 2 radical 2 over that. And now you see, if this is 2 radical 2 over 2, maybe you want to rewrite it this way. Okay, so now you see 6 over 2 gives me 3. 2 over 2 gives me that 1 times my radical 2. Is that all right? So that's the logic, that's the reason of when you can cancel and when you cannot cancel if you're writing it as one singular fraction. Okay? So just be cautious that I get the number. That's kind of the number one error I get when I ask people to simplify. They have this, but then they just start canceling things incorrect. All right, so just be cautious of that. Do you guys know what that radical 37, what the number 37 was called? If we go back to maybe last year's. Okay, it is a prime number, so it's not gonna simplify in regards to radical. Let me ask this. Let me phrase it this way. So we had x equals the opposite of b plus or minus b squared minus 4ac all over 2a. Maybe the way I phrased that question wasn't great. That turned into 37 in the last question, right? Okay. So you ever remember what b squared minus 4ac is called for the quadratic equation? Okay, it's the discriminant. Okay. And when I say I'm going to discriminate between two people, a lot of times people think that's a negative. There's a negative connotation with that word, but it's not. Okay, it's just saying there's a difference. Okay, there is an obvious characteristic difference between this thing, maybe item number 1 or object number 1, and object number 2. Okay, so for quadratic equations, that is the discriminating feature that tells me how many solutions I have. Okay, so it discriminates on how many solutions you have. If that number is positive, okay, if that number is positive, and down here in a little bit we'll write this in. I guess we can write now. If b squared minus 4ac is positive, greater than 0, how many solutions did we have in the last question? 2, right? We get 2 real solutions. Okay? If b squared minus 4ac is 0. Okay? Think of that last question. The last question was negative 5 plus or minus radical 37 all over 6. If that 37 would have gone to 0, what's the square root of 0? 0, right? What's negative 5 plus 0? Negative 5. What's negative 5 minus 0? Negative 5. So both situations, plus or minus, you still get a numerator of negative 5, right? And your denominator stays as 6. So how many solutions is that? 1. If this number goes to 0, you're taking the square root of 0, which is 0. So you're adding or subtracting 0, which doesn't do anything to my negative b. So you get 1 real solution. Okay? 1 real solution. And remember, every quadratic is a parabola. So if I use the quadratic formula, I get 1 real solution. It's actually a double root, correct? Okay. So my other option is b squared minus 4ac is less than 0. Okay, if it's negative, think about what happens when you have square roots that are negative. What gets brought into the picture there? Yeah, your imaginary values, right? Your imaginary numbers. So those are non-real. Okay, so when we have my discriminant being negative, we have 0 real solutions. And sometimes they will say you have 2 non-real solutions. So if you have zero real solutions with a quadratic, that means you have 2 non-real. Okay, but that's the discriminant, and that number tells me essentially how many times I cross the x-axis. It tells me how many real solutions we're going to have. All right. That number also tells me a couple other things, and this is kind of what I was saying at the beginning of class, is that when I get done with the quadratic equation, I should be able to decipher whether there should have been another approach that maybe would have saved me some time. Okay. That last one was radical 37. Okay. If that radical 37 does not simplify to where the radical disappears, then the quadratic is the only way, the quadratic equation is the only way that you can solve it. Okay? If that radical does simplify, so instead of 37 under the radical, I got 36. That would have simplified, right? That would have gone down, that would be perfect square, it would have gone down to -5 plus or minus 6 all over 6. And now the radical is gone, correct? If the radical vanishes, that tells you the AC method would have worked, the maybe product sum technique would have worked. Does that make sense? It tells me one of those other techniques that we developed as maybe shortcuts would have been maybe quicker in regards to factoring. Okay? And I think those types of being able to recognize that stuff is beneficial in the long run. You might not see a benefit of it right now, but at some point in your math careers, knowing that logic, knowing that argument may pay off at some point. Okay? So, what our answer to the discriminant look like? I want to stop there, and I know, guys, I wanted to get to the story problems today. Not going to get to those. I think if we start this one, we're going to run out of time. I'm going to push back the assignment all the way until Tuesday now. Okay? This is just something that happens throughout the years, depending on the time frame and how many times we, or how many questions we have, or maybe we run out of time to get to everything that I want to talk about before I make that assignment due. So I'll just continually push them back, all right? So right now, due Tuesday, we will definitely get through all of the story problems that I want to on Monday. And then that Tuesday is the final day. That won't get pushed back anymore beyond Tuesday, all right? There are